So what we did last time was to quantize the electromagnetic field. So we now honestly, to quantize a field, what it means is so I told you how this is generally done. So did I forget this here? Looks like mine. Because I brought another today. So the standard way is to say, okay, I say, what is the Lagrangian? If you need a classical Lagrangian, and a classical Lagrangian is written in terms of some generalized quadratures, not quadratures, coordinates q and velocities. And then, okay, why do that? Why start with the Lagrangian? Well, basically I need the Hamiltonian. But I do that with some Lagrangian like that. Why do I want to do that? Because this will allow me to find the momenta. So if this is a general coordinate, then by moving to, we can identify the momentum of, I don't know. Of course, there could be several coordinates, and then there would be several momenta, but is this. And those, it doesn't matter what Q was. Q does not have to be distance. It can be an angle. It can be even a field. Because when we think about the Lagrangian of the electromagnetic field, the Lagrangian is, well, the total of potential energy minus kinetic energy, and the potential energy includes the field squared, and the velocity, or whatever that would be, will also include something that has to do with the derivative of the field. Or basically, we can really show that in the classical electromagnetic Lagrangian, you can say that the electric field is the coordinate, and the magnetic field is the velocities, because the magnetic field goes like the derivative of the electric field. It's briefly saying, so in our case, these are not these are okay. So these are they don't have to be really coordinates of space, even. But then the point is that this is a general coordinate, and this is the canonical momentum that is conjugate to the coordinate q. then you can write a Hamiltonian, which is a function of P and Q, which is the, not Laplace, sorry, Legendre transform of the Lagrangian, which is just P Q dot minus
sigma over the PQ.
what?
You have only one Q.
I'm sorry?
Sigma over the PQ dot.
Yes, of course. I mean, right now I assume just one coordinate for simplicity, but of course, generally there are many. There are many of those, and there are many of those, and then here I would sum over, I don't know, J Pj Qj dot minus the Lagrangian of. And then we will get the Hamiltonian. Of course, and the process is, of course, when you do that, you use this relation to express qk dot using pk and eliminate it from everywhere, so that you will have an expression of p and q and does not have q dot. And then you have a Hamiltonian. And now you can, and the quantization now says, okay, I enforce this. I say that P and Q are operators and not. So that's the quantization step. Is to say that those are actually operators and that they have the standard commutation relation. And from now everything, and now you can write therefore the Schrödinger equation is correct, and you can continue with any quantum picture you would like. Schrödinger, Heisenberg, you choose. So, and then cannot say that. I h bar psi dot is the function of q equals the Hamiltonian operating on psi, of course. Important to note again that this wave function is a function of the coordinate. So when I write the wave function, I express it in terms of the coordinate that I choose. Now the question is, okay, so what is this? Normally you're used to, from standard quantum mechanics, that this is, I don't know, space. But as I told you, what plays the role of the coordinates for the electromagnetic field are the fields themselves. So it's not, when you need to forget the thinking that the quantum mechanic oscillator oscillates in real space. What I mean is, okay, if we think about a string, well, a string has eigenmodes, just like the electromagnetic field. Those modes have eigenfrequencies. Each of those modes is an harmonic oscillator. What oscillates? In this case, what oscillates is indeed the string up and down. When I think about that, so what does when you have an oscillating, like, I don't know, an oscillating string, then if this is the location x, then the oscillation is this. This is psi of x. And that's what oscillates. So really you can say that, so here what happens is that x is just a mark for the distance, for the axis x. I mean, when I say, so in this case, what actually vibrates, what is the oscillating thing that should be then quantized? It is not this. This is just an index to say, where am I looking? What is oscillating is this up and down. And what we can say is that, look, if this mode is classical, it acts like a classical harmonic oscillator that oscillates at, I don't know, omega 1. And it will have energy of half omega integral over psi 1 of x absolute value squared dx. That will be the total energy, and for a mode this will just be a number that eventually is proportional to the amplitude of that mode. So it will go like basically half omega 1, so some amplitude absolute value squared. This would be a normalized, so this is basically just the result of this. Now, and quantum mechanically, this is in a way, the coordinate. In a moment, we'll explain what. I'll take another step to explain that. But and if we think about the electromagnetic field, then it's not an oscillation of something real, of a real spring in space. It's the electric field and magnetic field that are oscillating, have oscillating values in space. So this wave function as a function of q. No. Or wait, let's complete this analysis, an analogy of the string first, and then I'll go back to the electromagnetic field. So that here, so I wrote this energy here, and now we can say that like qx, meaning that the q at x is psi at x, the amplitude of the oscillation at x. And what is okay, so p of p, where x is like an index. It's exactly like here I told you, look, there could be many such coordinates. They would have an index. In this case, p is going to be something that has to do with the mass density and the tension of the, but that's not very important. And here that would be psi dot of the same x. So this x has nothing to do with p. This x is just the index to say, where am I looking at the oscillation? And and eventually we can, and then we say, but now we can break any general oscillation. We can write this psi of x as a sum of, I don't know, ui of x. And then those are modes. And I don't know. that have some omega I t with some or maybe cosine or sine, so we can say that these are modes. And then we say, and in that case, we can say that the total energy, which is basically generally this, okay, so it will be something that will include something like that. It will be a sum over modes. Well, and then there will be some half omega I and AI absolute value squared, where those are the amplitudes of each mode for each of the modes. And now we say, and we understand that each of the modes acts as a harmonic oscillator. And now we can say, well, okay, so every mode by itself is a harmonic oscillator. Now I can assign a single coordinate to it. What is it? It's amplitude. So for every mode, the x component now is gone. I no longer need, the x coordinate was just like an index telling me where am I looking. But now when I move on to describe the field as a sum of eigenmodes, all I need are the amplitudes of each mode. And this amplitude acts as the one coordinate of that mode. So, and in here, we can also identify, so this is, the problem is that the way this is written, it is not written as p squared plus q squared, but it is actually written as, well, we know that the harmonic oscillator, Hamiltonian, can be written, Hamiltonian of the harmonic oscillator can be written as something like half omega squared p squared plus q squared, something like that. Well, forget, or of course this is, we should be a little bit more careful, but and it can also be written, and this is actually correct, as half h bar omega times a dagger a, or h bar omega times a dagger a plus half. So, excuse me, I'll take that away. I don't want the halves right now. So, and then, and the main thing is that I can, if I know the harmonic oscillator Hamiltonian, then I can write it in terms of P and Q, or I can write it in terms of A and A dagger. And the fact that I quantized P and Q and said that these are quantum operators who have a canonical commutation relation, this is exactly equivalent to saying that the commutation relation of A and A dagger is 1. Because A is simply Q plus IP. And if you think about that, for the real harmonic oscillator, this is simply what we would call the complex amplitude of this, and as we said, classically, the trajectory of a harmonic oscillator in the QP plane is simply a circle of amplitude A with a phase that depends on time. So what happens to this one? Well, the same. The whole spring is oscillating up and down. At this position, it has only Q, no P. So we're here. When it passes through the center, it has only velocity, but no momentum. So this. And once we do that, so we identify this as a sum of such terms. So this becomes sum of I. So this is the quantization step. That's the quantum step. So to say that this is a sum of I of what? H bar omega I times AI dagger AI. If you want plus half, the half is not a critical part. Or you know what, I can do something different, and that is to say, let's put a half here, and here make it symmetric. That's okay. Because, well, of course, this is another way to write the same Hamiltonian. So now we know also what to identify. We understand that the complex amplitude, in this case of the string, the complex amplitude of the string being the fact the string, of course, has an amplitude and a phase. So therefore I can combine that into a complex amplitude, and that complex amplitude represents what? Well, it holds all the information about this mode, which is how much it oscillates and at what phase. And as we just understood, this amplitude, this complex amplitude, is analogous or is quantized into the creation or annihilation operator of the relevant harmonic oscillator. For us, what is oscillating? There's nothing physical oscillating in space. It's the electric field that is oscillating in space. And therefore, the complex amplitude of the electric field is going to be related to the creation or annihilation operator. But let me say something a little bit more. Let's think a little bit more about the string in real space. So the string in real space, we feel still a little bit convenient about it because it is, what is vibrating is real. So we see a real vibration, and we say, okay, it has an amplitude and a phase. And then, what are phonons? Well, we can talk about photons as well in a moment. But what are the phonons of that string? The answer is the fact that each of those modes, acoustic modes of vibration, they can be either at the vacuum level, meaning at the minimal energy at this, when this number is 0, and we have only half h bar omega of energy, and that is what? Well, that means that this string that should be just sitting there doing nothing is actually fluctuating, really fluctuating. And we don't know exactly where it is. It could have some amplitude. I don't know what it is. It could be positive or negative. And it will have some momentum. I don't know what it is. On average, it's zero, but it has some uncertainty. And that is the vacuum phonon state of that standing mode. And we can think of that mode as being occupied by a single quantum state, by a single quantum of energy. What? Acoustic energy. Note that then it will have a wave function. But it will be a wave function of what? It will be a wave function of, so in this case, this A is the complex amplitude of mode, of the mode. And we can say that, when I say that that now I have a problem, which is that I made a mistake. I called the amplitude here psi. We usually like this letter, but when we do waves, that makes sense. But now I want to use psi for the quantum wave function, and I'll run into trouble because I'll use. So I do the simplest thing of all. We'll call it something else. Not you. I don't know. Give me something.
Theta.
Okay, it can
You
be
asked
theta.
for something.
Yeah. Okay. Let it be theta of x. So the point is that now the quantum state or the wave function psi is a function of what? Is a function of the amplitude of the mode. If we said that this is the quadrature, so it's a function of now the quantum x. But the quantum x has nothing to do with this x in space. It's the operator x, which is a plus a dagger. And that is. So, and this x is actually, well, a plus a dagger is just the real part of a. If this was not an operator, but if this was just a classical amplitude, then yes, x is the real part of a. That's what q is. So when we say x here, the operator x, and here I would say I would say psi of one phonon. This is the Hermite Gaussian, this is the h1 of that x times e to the minus x squared, right? But what is that x? This is important to understand. This is not. I can think of this I can think of that I can think of this, but this wave function does not live in real space because its coordinates are not the coordinates of space. The coordinates of this wave function are what you would call, the coordinates of the wave function are what is classically oscillating. Okay? So what is classically oscillating is the mode. So the amplitude of that mode is related to the coordinates of quantum mechanics. The position x, the real space position x, is not oscillating at all. This is just a localizer, an index to tell me, okay, where am I? This mode, this electromagnetic mode, is a continuous mode. It's not a single oscillator, it's a continuous mode, so it is, I don't know, the mode has a mode density in real space. So, okay, so this part is important to understand. And this thinking of the string is something that is important to internalize. This is something that helps, because I'm going to tell you that, yeah, that like in light, what is written here is basically the field itself. Okay. So I think, so let me remind you again that okay, so now I'll be quick with the case of the electromagnetic field, just to write the relations between, indeed. So as I told you, what is oscillating are the electric and magnetic field, and in a way they're combined. So they're actually combined into the electromagnetic field. So they are, if you know the field, the electric field everywhere in space, you immediately know the magnetic field everywhere in space. So we only need one of them, and they're all related to yeah. I don't want to do everything again, so I'll say something like okay. So for the electromagnetic field, we remind ourselves that we can use we can choose a gauge and we have this is, everything is derived from that, and E is simply Now there should be a scalar potential, but we can do that in a and how this is done, this choice is generally possible, and the equation for A let me be is just the wave equation. Sorry. And from that, we know that A, the general solution for A of R and T equals, can be written as a sum over K, and those are, and in a moment I'll remind you what those K's are, of A, K, and lambda, and T times E, the vector depolarization E, A lambda, and K X, Y, Z equals some 2 pi over L X or Y Z times some number. So and which can be written as sum over K, again E K, this, and here we will have A K, and now this is just a complex number, it's just the amplitude times e to the I K dot R minus omega K T plus A K star times the same. And we know that this omega K is simply c, the speed of light, times absolute value of K, which is taken from there. So here, you know, and all that is classical physics. And if you remember, and of course, there's a quantization here. We're quantizing the modes. But this is classical. The fact that we have electromagnetic modes is a classical fact. They're discrete. Well, because we have some boundary conditions that dictate the discrete modes of the problem. And given this, once I have this expression for A, we're still classical. I can write, okay, therefore I can use these equations and say, okay, the field, the electric field, also can be written this. So E of R and T, the general electric field, this is equal to what? Again, sum over modes. And here we're going to take derived by omega, so we're going to have here just I omega K times, sorry, times ek lambda. This is the polarization vector. And then what? Ak times e to the I. Same. And here minus ak star. So we expressed now, if I know those modes, then any coherent summation of those modes will make a vector potential. And from that vector potential, I will immediately extract the electric field or the magnetic field. And here, instead of that, would be IK cross E. By the way, this is sum of K and lambda because there are two polarizations. Lambda is the polarization. So I should, this lambda here is to say, okay, we have, the electric field can oscillate. At point X, we can have an oscillation in the Y direction or in the Z direction. So therefore, this is this is for the polarization. And here we have this, and still the same. So here I'm not going to actually even write it. I'm going to just copy it. So the electric field and the magnetic field, given the potential, are almost the same, because I mean the K, the wave vector K and omega have basically the same length. So this has, okay, so the difference between those is just the speed of light in terms of magnitude. And in terms of direction, then they are orthogonal to one another, because this one is at the direction of the polarization, and this one is orthogonal to the direction of the polarization. And now, and the last thing that we last time did rather quickly was to say, I know so that classically the total energy of an electromagnetic field is, I don't remember if we need the half, but the half is not the important part. Integral over the entire, I don't know, the volume. It's a volume integral of what? Of E squared plus B squared. Now, that's okay. So, okay, now I can just take those and put them there. It's going to start messy, but very quickly it becomes simple. Why? Because it's E squared. So there's going to be a double sum here for K and K prime. And here there's going to be a double sum also for K and K prime. And we will have elements that go like, so we're going to multiply this, which is a complex function, by its conjugate. And this one by its conjugate. So we're going to have, so here we will have expressions like, so that will be normally a sum over K and K prime, and lambda prime. So it will be a double sum, of course. But we will have here things like, there will be elements that look like A K times A K prime star, multiplied by e to the I k minus k prime dot r, and another one probably times e to the I omega k minus omega k prime t. Now forget about the t part because we're integrating over real space, and therefore these, when you integrate over the entire volume, then this will become, when we integrate over volume, this will become a delta of k prime. And that will kill one of the sums. Immediately it will kill this one as well, because if k and k prime are the same, then omega k minus omega k prime is nothing. So that's, of course, we will have many terms like this. I didn't write it completely. So and because of that, so that kills this sum. So that becomes just simply the sum. Now let me write it correctly. Yeah. So we'll have half. There will be the permeability, the vacuum permeability times the volume times what did I forget? Where are you? Yes. Times omega k squared times, and then here we will have yeah. So I'll tell you why there was a half here, because here I want to write something like AK star sum over k and lambda plus AK lambda star AK lambda. Now, actually, this half here, I could have, those two classically are of course the same, and I could have thrown that half and just wrote here AK absolute value squared, but I chose to write it like this. Why? Because now I'm going to do the quantum step, and for the quantum step, I know that the order matters. And I know that what brings me the right, so now we're going to do, this is the quantum step, to say that what is actually happening here is that the electromagnetic Hamiltonian is indeed half this epsilon 0 volume times omega k squared times what? AK dagger AK plus A k and lambda. And now those are operators of what? Of what? Of quanta of energy. Where? In the electromagnetic field. In the field of the mode K. So just like a phonon is a quantum of acoustic energy in the real vibration of a spring or a string, a photon is a quantum of energy in the oscillation of the electromagnetic field. And now when I said that, I can immediately write the quantum so like I can go back here and I can write the expression for the quantum operator for the electric field, because every physical quantity will be represented by a quantum operator. So if the field is a physical quantity, it will be transformed into a quantum operator. Now there is, there's a field. I can ask myself this: the electric field at location R and T in space. Now this is true. This is a quantity. This is classically, at every point in space-time, there is a value for the electric field. Now, so I want to say, okay, that is replaced by an operator. What is that operator? Well, it is written here already. So it's going to be basically, let's see, there's just one, where's a normalization point or something that, I want to get the expressions at least once right. Yeah, okay. Sum over k and lambda as always. And then what? Then this is the quantum, again the quantum step, or going quantum by this. So this is okay, there was something that should have been a little, when we went from here to here, there was one thing that, let me just try to be a little bit more careful because I should have been. Okay. There's one thing that I made a small mistake. I went very quickly, but if you remember, the quantum case doesn't have that. It will have just h bar omega k. So now we also know how to normalize. That means that epsilon 0 v omega k squared times units of this, because those are unitless, right? They are creation and annihilation operator. They don't they don't have any units. So the units are absorbed here, and there's going to be a normalization factor between them, and that is the normalization factor that is now I'm basically saying, look, h bar omega k times this should be equal to epsilon 0 v omega k times the units of the vector potential A. Vector potential does have units, this one does not. So that gives us a normalization factor that will appear now, and I'm going to write it. Where do you go? Come on. I had it just a moment ago. Here. I square root of h bar omega k divided by 2 epsilon naught v times, that's the normalization that is necessary to make that, and then here we will have just a k lambda e to the I k dot r minus omega kt minus a k and lambda dagger e to the minus I, the same. Now, so now look, and I can call this. So that is the creation of a photon in mode k and lambda. That is the annihilation of a photon in mode k and lambda. And this entire thing, without the sum, is something that has to do with the... This is an operator. We can write it. But now what does it mean? Let's just look at that. I'm looking at just a single mode. So, for previously, we just could say, look, if I think of a string, then this function is simply the mode structure, right? I know. And now if we okay, so you know that okay, so now I would take a look at that. And say, well, the electric field, I say that it's an operator. No, it's not an operator. It's many operators. At every position in space-time, it's a different operator. At some locations of space-time, I don't know, wherever this phase is 0, then it's like A minus A dagger times I. So then it becomes what I would call P. And then at other locations, or at a different time, or at a different location, then it becomes, it will be A plus A dagger, and therefore it will be Q. So the field of a mode is, as a function of real space and time, is changing between Q and P. and some variations of them. So it's constantly moving between all kinds of superpositions of Q and P. And that means that the field does not commute with itself at a different location. So that means that this is, okay, so like this can be like when k dot r minus omega kt equals 0, then ek at that time is simply I ak minus ak dagger, which is like P momentum, and when k dot r prime minus omega kt prime equals, I don't know, pi over 2, then this is an I. So then E k of r prime t prime is no longer I. Goes like ak plus ak dagger, which is x or q. So that means that under this or and so in that case E, K, R, and T, the commutation relation between this, and it's a different operator because it's going to be a different location, that is going to be, I don't know, IH bar. It depends on, that has, the I is critical and the H bar is a question of normalization. And we're going to use, for convenient, we're going to try to forget about H bar. And I can write this. So I can even do more than that. And I can write, and now I'll break it here because this is useful. I can write the following. The field is just, again, sum over k and lambda. And now instead of A, I'll remember that, so I'll have here the same thing, square root, in this case, and here I'll write x operator of k lambda times cosine, and then we'll say something cosine of k dot r minus omega kt. And just okay, plus y k of k and lambda times sine now
K instead of Y.
What?
K instead of Y.
Indeed, yes. So, and they are defined like that because their relation x, the relation between x and y, of course for the same k and lambda, is just I. So these are, so you can see that now we can actually identify who are x and p. And as we, in a way, as we expect, x is the amplitude of the cosine component of the oscillation. And y, or p, is the amplitude of the sine component of the oscillation. Now, any real field that is oscillating in space and time can be written as a sum of a cosine and a sine. And now what we tell you is that, look, you cannot know both. And those are the quadratures. These are, so x is like position, and that is the real quadrature of the field. And y is like momentum, and that is the imaginary quadrature of the field. Okay. So, I want to start looking into the we're going to describe a single mode from now on, and we're going to do several examples of that, but I need a break. There was one thing that I forgot to say, and that is and this is to remind something that is always, of course, classical. That is that we wrote that this a k of lambda, this function of r and t, we said that this is actually like now when we write that, we assume something about the boundary conditions, and this is not very much of a physical boundary condition. You remember that, okay, we can say that, A of R and T equals sum over K and lambda. But, so this is general. But what those functions are, that depends on the boundary conditions that we assume. Okay? Sometimes, like if you have, like in a cavity, then those would be like a cost, depending on these, are these open boundary conditions or open or closed, or no, Ketzer and Netek. Never mind, but we need to define these can be either like those functions. They could look like sine. So this is in a cavity, in a general cavity, and they can be look like a sine of k dot r, or cosine of the same, or some variation of. And in the case of assuming periodic boundary conditions, this is the solution. This is for periodic boundary condition. Why go for periodic boundary conditions? Because then it behaves as if you have a field that is propagating in space. But remember that the fact that the modes are discrete means that there are boundary conditions, that you assume that there is a finite space in which we quantize the field. So in the assuming periodic boundary conditions, the mode functions are just traveling waves that are either traveling forward or backward. That's why we had. So and here indeed, like and as we said, there's okay. So then, okay. So if I want to think inside the cavity, then say that we have a cavity and then we have metallic mirrors at the edges, but these are perfect metallic mirrors, superconducting mirrors, so that they have a reflectivity of 100%. And at that case, that means that on the mirrors the field is zero. So the electric field in that case is just like a standing wave, a sine standing wave, the standard way you know. So we'll have the fundamental mode, the second, and so on. There can be modes to infinity. And then, if I think of a given mode, then this mode has nodes. When I talk about the amplitude of a mode, the mode has a fixed structure, and now I ask myself, in that fixed structure, how does it oscillate? So that mode, for example, has nodes where the field is just zero. So this fact is not going to change. Like if you sit inside the cavity and you put an atom at the node of the electromagnetic field, or at the node of a mode, then this atom will never absorb light, assuming that this is the frequency that it absorbs. Why? Because there's no light there. There's zero light. You're sitting at the dark point of that standing wave mode. Okay. So now okay. Oh. So I want to talk about no, this one doesn't. The blue one writes better. So I want to say something about, so first, the states, the quantum state of a mode. And we can start with the simplest quantum state of a mode. And that is to say, I can say that the state is vacuum. So, and then now so now we can ask ourselves, okay, what is, so assuming that, that mode is there's no light there, so the electric field is still in a vacuum state. And then I can ask, okay, so what is the average electric field for the vacuum? Well, we know what that is. We write that. Now, when I say E, I should ask when. But let's assume, like, when and where. But as I told you, so in general, what is going to be written here, so is, if I want to be a little bit more exact, then this is 0, and then here, let's assume that in space we are at location 0. So this is basically A. Now I'm going to be of it's a single mode. So I'm going to drop the K and lambda. And this is just A e to the I omega t plus A dagger e to the minus I omega t. Now, honestly, it doesn't matter. So say we choose R equals 0. So we're looking at but, well, of course, you know how to calculate. That's why creation and annihilation operators are convenient, because when we know what happens when we operate them on vacuum, and this is going to be, of course, 0. Because either you operate with the A to the right and annihilate and annihilate the state, or operate with A dagger to the other side, which also annihilates the state. But if I ask what is the average of E squared for vacuum, now that's no longer the case, because now there's vacuum here and there, but here we have A plus A dagger. I can leave it like that, squared. And here we have, okay, we'll have vacuum, and here we'll have A squared plus A dagger squared, and those will be 0, plus A dagger plus A dagger A on vacuum. And this one will fall, and this one will fall, and this one will fall, and you know why. But this one will give us 1. So this, the average field squared, is non-zero. Has a value. We can bring back the correct units. So basically, like I'm saying that this what brings in the units, basically times the 1 that we just found. So there is, so this is a funny case. Okay, so far maybe we're not surprised because we know that about, well, I just told you, look, the field is like position or momentum or both. And position and momentum have an uncertainty, so average of x squared or p squared is non-zero, so that's not surprising. But what is a little bit more surprising is the question, okay, so, you know, classically, you can never okay, what I want to do now is to ask, okay, what happens if I put a detector in front of the vacuum? Okay, so remember, classically, the question of how much energy is in a mode and what will a photodetector register, they're the same, right? I mean, if there is energy in that field, when it hits the detector, there will be a photocurrent proportional to that energy, and this will be recorded. And now, so we want to ask, so okay, so there is, it seems like there's field, and then there's, of course, there's energy, like the U equals half h bar omega for the same thing. So there's energy in the vacuum. Well, you could say, well, but you know, energy is not, it's defined up to a constant, right? So I can, that's just a constant, so I can throw that out. Well, yes, but you have infinite number of modes, so you're throwing away an infinite energy. But never mind. What I want to ask is, okay, so what happens when? So I want to discuss for a moment the. So, what will a photo detector register? Now, the point is that we are now standing at a funny situation where on one hand, we know what is going to happen. Well, if I put a detector in a dark room, it does not click. Well, classically it makes sense because in a dark room the field is zero. But we just realized, but we also remember that the detector responds to the absolute value of the field squared. That's what it responded to. And now we realize that the absolute value of the field squared is non-zero in vacuum. So how come photodetectors register nothing in vacuum? Classically, we cannot understand that. So here, and of course here, that's where the non-commutativity of operators come to play. So if I want to talk about the quantum photo detector,
So
and this will, what?
in reality, if the detector is רגיש מספיק, it can see the fluctuation.
No. Those fluctuations are virtual. And I'll explain in a moment, but the answer, but the quick answer to make the puzzle even deeper, the answer is yes, those fluctuations are definitely there, but you can never detect them. Or at least not directly. If you put just a detector in vacuum, it will honestly never click. You can detect them indirectly. You can detect their influence in some cases. For example, like, you know, if I take a beam splitter and I shine light on it from here, and then some light will go here and some light will go there. Classically, you just disregard what comes from here because nothing comes from here. But what actually comes from here, in the case that nothing comes, is vacuum comes. Vacuum enters the beam splitter from that side. And therefore, if you remember what a beam splitter does, it takes here, it puts the sum of the fields, and here it puts the difference of the fields. Okay, so you'll have, I don't know, you'll have maybe a perfect field here. But here you will have that field plus the vacuum field, which is fluctuating. I don't know what it is. On average, it's zero, but it has some fluctuations. And here you will have the field minus the vacuum field. So I don't know what the phase of that vacuum fluctuations are. They're random, but sometimes they would be constructive, and sometimes they would be destructive. So they will introduce noise, and they do. So and whenever you see constructive interference here, and this one must be destructive because they're plus and minus. So that means that even if you could make a perfect classical field that has a perfect classical constant amplitude with a perfect phase, what you will see here, quantum mechanically, is that there will be fluctuations. This intensity will fluctuate, and you will say, why? Because vacuum entered the beam splitter from the other side. That is to say that classically a beam splitter generates two perfect copies, right? A beam splitter, if you throw in A, here you'll have A over square root of 2, A over square root of 2, perfect copies. Quantum mechanically, no, because here you have A plus whatever vacuum is doing, and here you have A minus whatever vacuum is doing. So this introduces differences. The fact that this one is coming with plus vacuum and this one is minus vacuum, and this makes the situation, and you don't know what that vacuum is. So that means that those two copies are no longer actually equal. They're not identical anymore. So there's relative noise. If I put here two detectors and I take the difference between them, classically, I expect this to be zero. No matter what is coming here, noisy, not noisy, doesn't matter. Those two are equal, detect, boom, zero. Quantum mechanically, no. Because if you take those differences, and again, I don't care what comes from here, this vacuum is going to make this thing noisy. So that is an indirect way to measure the effect of
how
of the
they
vacuum.
proved it?
What?
This is how they proved it.
What?
The vacuum fluctuation.
There are many ways to actually see the vacuum fluctuation. Let me tell you,
Let's say what they thought before they found the vacuum fluctuation.
let me tell you what is the problem that could not be solved before and now actually is being solved easily. The main thing is spontaneous emission. If you remember, we discussed, we talked about the two-level system, and then we had to, and if you have an atom in an excited state, we introduced a decay, but we introduced it by hand. We had no reason. We didn't know what the mechanism was for that decay to happen. We did see that if there is field, there could be absorption if the atom is in the ground state, or there could be emission if the atom is in the excited state. So stimulated emission and absorption are well understood classically. And then we can ask ourselves, but spontaneous emission, where did that decay come from? Why does the excited state decay? And the answer is because there are vacuum fluctuations. The field, even when you don't have anything in there, this atom feels vacuum fluctuations. And this is like a field, and it can stimulate it down. So the fact that, so in many ways, and we'll see that later, vacuum, the quantum explanation for spontaneous emission is that there's no such thing as spontaneous emission. There's only stimulated emission. But when you don't shine light, vacuum is there to stimulate the light. And if you can engineer the state, the space such that there will be no vacuum field at the atom location, then this atom will not decay. Never. Let me tell you how that can be done. The atom has, suppose that now I take the atom and put it in a mirror box. So it is sitting in a small box of mirrors. And the mirror box is such that at the mode that is at the frequency that the atom actually absorbs has a node somewhere, let's say in the center. So at that point, because of the fact that this is a closed real cavity, then at that location in the cavity, the field of the mode that the atom can absorb is zero. And because those mirrors are perfect, there's no other mode. I mean, everything else, whichever field that comes from outside, will hit the mirrors and be reflected. It will not. So inside, there's whatever is inside. Nothing is let in from the outside. And then, okay, so suppose that I leave the atom at the node of that mode. Conceptually, it will never decay because there's no... The vacuum fluctuations are the vacuum fluctuations of the mode. This mode has a node where the atom is sitting, and therefore it will be... We can suppress spontaneous emission, ideally to zero. On the other hand, I can on purpose just move the atom quarter of an optical cycle, and put it at the crest of the field, and then you will maximize spontaneous emission. Because then what happens is that vacuum of every mode is always of energy half h bar omega. But the question of what is the field? The field, how strong is the field really is related to how big is the volume, because the field is divided by the volume. So if I ask myself what is the amplitude of vacuum fluctuations where you are at the maximum of the field, the answer is the smaller the mode, the bigger it is, because you have this half h bar omega to distribute over a smaller space. And then spontaneous emission will be accelerated. The lifetime of the atom will depend on where it is standing inside the cavity. And such experiments have been made and have been shown that you can both suppress and enhance spontaneous emission by engineering the vacuum mode. You engineer the mode and then put nothing in it, and that's still enough.
And you choose it by the boundary conditions.
Well, yes. I mean, you can, yeah, the boundary conditions, as I said, the boundary conditions dictate where that location is. So yeah, I mean, assuming that I have perfect mirrors where the field is 0 on the mirrors, then you know how the modes look exactly. So I wanted to say something about the quantum photodetector. And so now, but now we already know what a photon is. So, when I ask myself, okay, so what's the quantum photodetector? So I need to think about the photodetector itself as a quantum thing. The detector has a state. Say it was initially in state I before detection, and then it transformed to another state F after detection. Why did it transform? And specifically, let's be specific. What is this state of it? What is a detector? It's matter. What happens? What is photodetection? Absorption of light. We need to, in order to detect, we need to absorb light. So this is the state before detection can be like the ground state, and this can be like the excited state. Now I should be a little bit more careful because a detector is not a single electron, it's not a single atom. There are actually many atoms in a detector, and I don't know, and one of them got excited, or one of them got ionized, one of them released an electron due to the interaction with light, and this electron is what I detect. So the detector state changed, but also the light state also changed. It had some, I don't know, for the light state there's also something like, I don't know, psi initial, and finally there's and when we think about, and what is the transition here? So here there was absorption, and here there must have been annihilation of photon. Energy was transferred from the light to the matter. Now, and I can ask myself, and now we can ask ourselves, the question is, what is the probability for the transfer? Now notice, I don't really know anything about the state of the light. I don't know what it was before, I don't know what it was afterwards. All I know was that, because what I follow is the detector. I see that the detector changed its state. So that is the probability for the detector to go from initial to final. Now, I'll be careful with that. So, okay. Now, classically, a detector responds to the field intensity, because that is the energy density. Energy density and field intensity classically are the same at the location of the detector. Right? I put a detector here, it will respond if the field here is non-zero. So I'm looking for something that would look like this. Now, but quantum mechanically, this can be either A dagger A or A dagger. They're not the same. So the question is, which one of them should I use? And let's explain this in a little bit more rigorous way. So if the detector location is, I don't know, some, of course R and T, but that detector, I'm asking what's the probability for a detection around in the vicinity of this, like the probability for a click at that point in time, at that location in space. And so that will go like E of R and T in a way squared. So I will need to define what that means. But let's just remember that quantum mechanically E of R and T is, okay, sum over K and lambda, what? We have here a normalization that I don't care about, times A, K, and lambda e to the I, K dot R minus omega T, plus A plus or minus, but now, well, that's the general field. But this part annihilates. It's a sum of annihilation of all modes. And in a way, I could think of this as this sum of K and lambda and that part is what tells me I'm going to annihilate a photon at location R and time t. I can say, and this one is all creation. So I can define two operators. One of them is called E plus of R and T. And one of them is called E minus of R and T. Now, normally you would expect that the one that goes with minus will be the one that actually takes away a photon and annihilates it. And the one that goes with plus will go with the creation. Unfortunately, the standard notation is the opposite. And I think we should find whoever that did that, and had he not been dead, we should have made sure that he will be. But the annihilation part is just this sum over K lambda A and this one so this annihilates at R and T. This one creates at R and T. Now we should take that with a little bit, with a grain of salt, because to actually be able to create a photon or annihilate it at a very specific location in space-time, at the delta function of space-time, that means that you will need infinite k's. This will not be, this sum is not going to be to converge in any way. But and now we can say that what happens is that this transfer is done by, this is what E plus does. So I can say well, yeah, I'm trying to be well, okay, I can say it in the following way. Did somebody teach you at some point perturbation theory? Okay. The atom, or sorry, the detector was sitting nicely at state I. Had there not been light, and there not had been any field, it would have kept sitting there. But then the field is there, and we look at it as a perturbation. Okay? So, and you know that in perturbation theory, E plus, that is the perturbation, and we can say, okay, so I was initially in state I was the detector and the light was in state psi I. It ended up in state F and psi F of the field. And why did it change? Because there was we had a perturbing field. The states I and psi I are states of without interaction, but there is interaction. What is this interaction? It is just this. So this E plus of R and T at the location of the detector. And what do I want to know? I want to know what is the probability. So this is the matrix element of the field between the initial state and the final state. And what is the probability of transition? This absolute value squared. That's the probability of transition from initial to final. Okay. So now I can say, okay, so now let's look at that. And that is now I look at that a little bit further, and that is actually this. So we have, okay, I'll term this entire thing I, both of them. And here we will have E plus, and here F. But and I want to look at this F. Conjugate of E plus is E minus I. So that's what this absolute value is, just that. This, if this is the matrix element of E, so this is the conjugate of that. Now, so now, actually, okay, now I can say another thing, and that is that I don't know the final state of the detector could be, as I told you, the detector is big, there are many atoms in there, I don't know which one of them emitted an electron and I don't care. All I know is that I have an electron. So in reality, what we should do is we should sum over all possible final states that lead to an electron. In reality, we should say, okay, I'm going to sum over all the final states in this case. That's actually why. That is because F is unknown. It can be, any atom could absorb, I don't care. All I know is that I have an electron. So So that means, and now you can see here, so sum over all final states of this, that's actually a unity. So sum over f of f, so that's just the unit. So sum over f like this becomes just the identity operator. So this is simply, tell me what the initial state was of light and detector. The detector was sitting there, light was, I don't know what it was. And then you should have E minus and then E plus. And that's the order. Why? And now you can see E minus is a dagger and E plus is A. So if you ask me, what is the probability to detect? I will tell you, you need to calculate the average of A dagger A and not A dagger. The order is important. So a detector, so that means that okay. So that means that the probability of detection, it's no longer the probability of transferring from I to F. I replace that. It's probability of detection, which is sum over the final state's probability from I to F, right? So what we had, so the probability of detection, which says, is simply this initial state of light plus detector, and then there's this E, what did we say, E minus, E plus. All right, now, but the state, but E is an operator that operates on the field. So in that situation, all I care about is basically just saying that tell me what is the initial state of the light times A dagger A so the probability to detect in mode, of course, it's not everything is proportional here. There's a proportionality factor. But so that is the number. And indeed, and for vacuum, the detection is 0, A dagger A 0, and that is 0. You will never detect. what is the difference? This does not measure E squared. This measures almost E squared. Because E squared average, which we calculated before, was the average of A dagger A plus A dagger. That's what we had there. So it's not the same. If you want, put here a half, just to make things look the same. But, the field fluctuations and the detection probability, they're close, but they're not equal. Now, yes. Okay. So now let's look at if now we know what the quantum photodetector does, and we realize that the probability of detection is proportional to the number of quanta, then we can now ask about what we call G2. Remember what G2 was? That was like I1, I2, that was classically divided by I average squared. And that was what? That was the situation where we had something like we had here a detector that clicked, and here a detector that clicked, and we multiplied them. And we looked at, and if you remember, so now let's say that so that means that okay, you know what, let's not have the beam splitter, okay? Let's think okay, so I don't want to have the beam splitter yet because we haven't discussed it and we don't have enough time to complete the discussion of that. So I have here, this is detector sitting at R1. This is a detector sitting at R2. There's a field here. And I'm asking, and given that field, there's light. On that light field, this detector can click, this detector can click. I'm asking myself, what happens? How will it happen that so there was some state. So generally, I would say there was in this case, so like I'm going to talk about G2, which means like we're going to discuss two detectors. So I have a detector 1. So there is the probability of 1 to detect and also 2 to detect. Both of them. What is that? Well, I don't know. Tell me what the state of the light was. And then each one of them does its thing. What is its thing? They both, if both of them detected, then both of them annihilated the photon. So what should be here is what we called E plus of R1 times E plus of R2. Both of them detected. And then, just as we did before, this is, the perturbation is, both of them detected. Both of them annihilated the photon. And what do we have here? E minus of R1 times E minus of R2. This field is, I don't know, it's going there and it's going there. So that means that this probability of dual detection is now, again, psi initial, whatever that state was, and then A dagger, A. This is what we're going to have. Why do I operate with the same? So first of all, it's clear that this is going to be the order. And why do I want to talk about just a single mode? Well, because, you know, what did I draw here before? I drew a field coming in and a beam splitter. So then this detector and this detector, they're in a way acting on the same light. If you, I don't know where the light will go, either here or there. So that's, and now we can see that, okay, order matters. So now we're going, and so now let's calculate that for several. Let's calculate this. That's going to be quick. For so that means that the quantum G2 is this. Tell me what is. So G2 is what? I don't know. Whatever the state was. Here I have A dagger, A operating on psi divided by what? By psi A dagger A psi squared. What did I say here? This is, we normalize, if you remember, G2 is the intensity correlation divided by the single intensity average. Normalized to the single intensity. So in this case, this is the single intensity, what a single photodetector will show. And that is the question of having both of them annihilating a photon together. Now let's calculate that. So calculate G2 for the state, assuming that the state of the light was exactly n photons. The standard, the harmonic oscillator number states. So if that was the case, then G2 for a number state what will it be? Okay, n, and then A dagger, A, n. Now you know divided by n, a dagger a, n. Now, what we have down below is simply, this is going to get just n squared. But on top, we have this gets n, this one gets n minus 1. Square root of, so we have here square root of n minus 1, and from the other side the same. So we will have here n times n minus 1. So that is 1 minus 1 over n. So first of all number states are non-classical. Why? They have g less than 1. g2 less than 1. If you remember, classically g2 could be only larger. Classically, there's Cauchy-Schwarz inequality that tells you that the top must be bigger than the bigger or equal than the bottom. So this is, that immediately says non-classical. But obviously, as n goes high, it's very hard to tell. But for n equals 0, well, n equals 0 is not interesting because no detector detects. But one photon, for one photon, then detectors will click. We don't know which, but they will never click together, and indeed, quantum G2 is 0. So that means that if you remember tau, now we actually saw that when you're detecting a single photon, then this will happen. That's the quantum prediction for a single photon for G2 as a function of tau. Now we should be careful here. If there's really just a single photon in the world, always, then it doesn't matter what you do, only one detector will click, and only once, and that's it. But the assumption here is that I have a single photon source that is emitting again and again and again. Now, during a coherence time of the photon, there will be only one. But after more than one coherence time of the photon, then you have a probability of exciting the atom again, it will emit again. So you do have a probability of coincidence when the time difference is large enough. But for 0 time difference, you have only one. So you see, so having G2, people say G2 is a quantum signature. Yes, but it's primarily a quantum signature of the single photon state. Any other state, it's very hard to tell whether it's going to be classical or quantum just by measuring G2. But G2 is a measurable quantity, and we can see if it is. Okay, yeah. Okay, so what we're going to do next? Okay, next week we're going to talk about coherent states. I think you know them, but we'll discuss them in the context of the most classical states that could be. And then we'll talk a little bit about the beam splitter and its properties and how vacuum does all kinds of fuzzy stuff with it. And then we'll talk about all kinds of, we already met non-classical states. The number states are inherently non-classical. There are many reasons why they're not classical, and we'll discuss that in various ways. But we'll also meet other non-classical states, and specifically we will introduce the squeezed states. Why? Because there are many non-classical states, but only one type of classical states that we can actually make in the lab. So those, for some reason, we discuss more.
So squeezed state is classical?
No. A squeezed state is the one non-classical state that is easy to produce, as opposed to number states that, well, you can make single photon states. It's hard. To make 2 photon states is even is harder, and to make 100, good luck. It is the probability is going to be something like e to the minus 100. טוב.
עדיף לא טוב. עדיף לא טוב.
הייתם באו? טוב יאללה בואו נתחיל לשיעור כיום. אוקיי.
אתה יודע מה התשובה.
Alright, so last tutorial we talked a little bit about the quantization of light and about some different states that are interested, like the Fock state and the coherent state, and then we define the displacement operator. And now I would like to talk about phase operator or phase states, something that's very ill-defined in the quantum mechanics. I'm not going to do the entire thing that there is in this tutorial notebook because I want to move on to quantum correlation. I'm just gonna show the problem and show why it's a little bit of a problem and what's so interesting about the phase, and then I'll also like draw you the different states that we talked about.
Quantum states of light.
Yeah, we're starting quantum state of light. We're just gonna touch it a little bit and then go on. Yeah, so last time we talked about the Fock state, which is a state where we have full certainty in the number of photons that we have in our wave packet. But in that case, when we have a fully certain amount of photons, we actually have a fully uncertain amount of phase. We know that, for example, if we have Fock state 4, we know that we have 4 photons. We don't know the phase. We don't know anything about the phase of that state. So there is some uncertainty, or there is an uncertainty between energy and phase in quantum mechanics. You can see it more deeply in the tutorial notebook, but let's try to see, even though there is such a problem and there is such a need for defining of a phase operator, why it's not that simple, and there is actually no fully developed phase operator in quantum mechanics. So, generally, every operator can be written in what we call the polar decomposition by A equals K times U, where U is a unitary transformation, right? And K will be equal to square root of A dagger, right? And now let's see what will happen if we try to decompose the annihilation operator, which is sort of standing for a number in the quantum mechanics. So with the same logic, we say that A will be equal to square root of A dagger times some phasor operator, which the exponent will be the unitary matrix and the square root would be K. Our decomposition here, and generally we'll define, I'll switch the order and replace the operator from annihilation and creation to the number operator. Right. Now we can easily verify that square root of n plus 1 would be equal sum over n equals 0 to infinity. square root of n plus 1. This is not an operator n. We'll state n. This is just first order quantization for this second order quantization term.
But the table is short n.
Yes, in the notebook, the original, they wrote it the reverse order with the AA dagger. I'm writing it like so to stay consistent with the definition of idea in the beginning. Also, you'll see that it will be exactly the same. You can just move the n1 space. It will be the same overall. And the phase operator here, this is arbitrary phase operator for now. This will facilitate, you see here, will give us the normalization factor, and this phase operator will need to facilitate the change from n to n minus 1 or from n plus 1 to n. So it will be equal to from n equals 0 to infinity and plus 1. Right? So overall, multiplying both of them together will equal sum over n, infinity, square root of n plus 1, and n plus 1. Overall, it will be equal to sum over n. This is orthonormal, so sum over n equals 0 to infinity. Square root of n plus 1. N plus 1. Hello. Bye. Okay. So now I've done all the steps, a little work, but I lied to you. I lied to you all. Why? Well, let's see what happens if we take phi. I told you that the decomposition here needs to be k some different operator that we transform to and a unitary transformation u. So d should be equal to 1. Let's see what it actually equals to. We'll have to sum and from 0 to infinity of n plus 1 m and n plus 1 should be equal to sum over n equals 0 to infinity n plus 1 n plus 1 which is equal, that's not equal to I minus 0, 0. Right? So it's not a unitary transformation. Note, although I would say note, if we take the reverse order, take the operator time the conjugate, the reverse order, the plus 1 would be in the middle here and cancel out, and we would get unitary, like it's a unitary transformation. This is called the one-sided unitary matrix. So the phase, defining some phase operator which facilitates transformation between nodes is a bit of a problematic transformation. There is a way around it that's not in the notebook, which I'm just going to note. You can define a unitary phase transformation for a finite size space. This is us trying to define it for an infinite size space by simply taking I equal 0, 1 plus 1, 2 plus n minus 1 n plus n 0. And then basically make it cyclical. And this would be unitary. And if we take n to be infinity, take n to be infinite, then we can actually achieve some proximity of some proximity of a solution for this problem. Yes, there is. let's actually do the example. I know we're not that much in a rush. Alright.
So we do the example.
Yeah, we'll do the example real quick. We might not do the end of it. I don't know, we'll see. You will prove, I'm pretty sure in your homework you'll prove more conclusively that there is no phase operator in quantum mechanics. Right. So, yes, so let's try to, just like we had a problem defining phase for an infinite size operator, we also have a problem defining phase for a phase state for an infinite size state, but we can do it for a finite size state, and this will be this example. We'll show you the homework, you try to see what happens when you take it to infinity, but so we'll define state with a well-defined phase phi to be equal 1 over square root of n plus 1, which is the normalization factor, sum n equal to 0 to n, e to the I, n, phi m, n, right? Or phi m equal 2 pi m divided by n plus 1. Right? Okay. So now you want to see that it's a legal state that we wrote. So first thing that we're going to check is that it's autonormal itself. So you want to see what's the result of phi n, right? So this will be equal to 1 over n plus 1, sum kl to 0 to n, e to the minus I k m k yes, so e I l m l, right? Now this is a number, so I can take it out, and we're only left with the term multiplication of these two terms which are autonormals. So we can reduce this sum to one sum. It's 1, sum over k equal to 0 to n, e the I 2 pi k n plus 1 n minus n. Right? Now this sum is a sum of arbitrary, large sum of arbitrary phases, which we know to be equal to plus 1 times the delta function. So overall, this n plus 1 plus with this n plus 1, so we get delta and n. So it is autonormal. Next thing that you want to check about this state is that it's complete. That by using the set of these states, we can get to everywhere in our space of possibilities. Basically, we want to prove m equals 0 to n, phi n equal to I, right? This thing would be equal to 1 over n plus 1, sum over m equals 0, n, sum over k l equals 0, n, e to the I k minus l, phi m k l. Right? Now this part of the sum would give us a delta function. So overall would be 0, n, n, n. Okay. Questions so far? From the big audience?
So those are only the eigenvalues.
What? What?
We get only the eigenvalues of the phase, right? Of phase M and phase N. Eventually we get only the diagonal.
Yes, eventually we'll get only the diagonal by multiplying them like this, which is the same as showing completeness.
Is it like to say the I matrix, like the 1 matrix?
So this is the one. This is the I matrix. This is exactly the I matrix. Okay. Now, do I want to do the next part? Let's do what? Let's do C and D. You can do at home just to save some time. The third product you want to prove, which is not really a proof that it's a valid state, but it's something interesting. It's another indicator to show that phase and the photon number are orthogonal, quadrature, orthogonal parameters of the field. We can show that by trying to transform the phase state around the number state and seeing what happens. So by that I mean, if I take the transformation EI n n hat phi L times the mod phi M, what will happen? Right. So this will be equal to 1 over square root of plus 1 n equals 0 n I n n p I n. Remember that by operating the n in the exponent on the Fock state comes here, you can just take the eigenvalue here because the n is the eigenoperator on the mode n. Right? So overall this will just be equal to sum of 1 over square root of n plus 1, sum n equal to 0 to n, e to I n phi n plus n, n or phi n plus phi n. So we see that basically the summation around the number operator rotate us perfectly in the phase state domain. So you can think about it almost like a vectorial multiplication. If the two vectors are orthogonal to one another, it will give you a perfect rotation on one another. Yes. You want to do part D, or do you want us to move forward and see that you have your
Do the
okay? So let us assume that we have some general state psi, which equals sum over n, n, right? You want to know what's the probability of measuring a specific phase. So how do we do that? Well, in quantum mechanics, to find probability for specific measurement, you need to take the, I'm intentionally putting a space here, you need to take the absolute value of what you want to measure times what you want to measure it on, absolute value squared. Now in our case, we took a finite n, but in reality we can have an infinite size n on the phi, so we need to add a limit here, and capital N goes to infinity for our phase state. And then we also have an n plus 1 divided by 2 pi for normalization here outside. It's not really important. Anyway, the absolute value of these two terms squared would just be taking the end, the coefficient of the end state times the coefficient of the end state here, because they're orthonormal. So we just have 1 over 2 pi times absolute value sum n goes from 0 to infinity Cn e to the minus I n phi delta y squared. Now we can check it for different cases of psi that we already know. For example, if we take the Fock state with n number of photons, right? We know that Cn is equal to 1 for the correct n, for this n, but equal to 0 everywhere else. So this would just be 1 over 2 pi. Because we're only going to stay with some exponent, and exponent absolute value squared is 1. Right? So we see that we have an equal probability to get every phase. And let's actually check the other characteristic to define any state, which is the average in the variance, right? So if we take this the exact same thing, so average, if we're talking about in statistics, we just need to take minus integral from all the possibilities for minus pi to pi over the probability to get every possibility, 1 over 2 pi times phi d phi times the characteristic that we want to average on, and cross integrate, and this would just be phi squared of pi minus phi squared of minus pi. So it's just going to be average phase of 0. But if we take the second order, just do it quickly, minus pi 1 over 2 pi squared d phi, this will be pi squared divided by 3. If we just calculate it, you'll believe it. Alright? So we see that the divergent. No, there's another word. First order. I forgot.
Variance.
No. Why did I forget? Static, yes. The standard deviation. Because that's the standard deviation. You see, the standard deviation will be pi over square root of 3. This number is not that important. What's more important, I believe, it's the probability of the phase. So before we go to the covariance set, let's see what it means when we try to draw the Fock state 1, for example.
שתהיה לך פיק ושווה 1.
No spoilers, that's the reaction. No spoilers. You remember last time we talked about representing states in the phase space, where we have the imaginary line and the imaginary axis and the real axis. We did this p x, right? So we know that the Fock state n equals 1 needs to have a precise number of photons equal to 1. And the precise equal photon in the phase space will be the distance from the axis. So it will be some distance 1, but we know that it can be at every phase equally. So it's just gonna be a ring. Just a ring. There's not really something here. It's a bit, yeah. It's gonna be a ring, right? Now what's gonna happen with the coherent state? The coherent state, yeah.
This is for the number state.
This is for the number state, Fock states, number states. For the coherent state, P alpha phi will be a bit more complicated, 1 over 2 pi. Absolute value of sum over n alpha n square root of n power e minus absolute value squared divided by 2 e minus I n phi. You remember we found this last tutorial. This is the coherent state. This is the coefficient of the coherent states. Alright? So overall, we get e to the minus what's the value alpha squared divided by not divided by 2 pi. Absolute value sum over n alpha e minus I phi square root of n or n squared. Okay. These we see that if yes, we can. I think you can develop it a little bit more. No, but this is fine. Yes, there's no more steps. That's good. Wait. We'll see that if alpha is very large, this term will fluctuate strongly, and only the term where why did I write alpha here? This is supposed to be phi. Only the terms where phi is similar to the argument of alpha. If I replace alpha here with absolute value alpha times e, I'm going to write alpha equal absolute value alpha e to the I arg alpha. Okay, it's it's the argument. It's basically the angle. If you put alpha in the again xy plane, it's the angle. Yeah. So only the terms where phi is close to the arg of alpha will not fluctuate widely and will not cancel out. So we will see that the probability will sort of focus on the correct phase of the alpha itself. We can develop it a few more steps that I wrote for myself in the notebook. It's really not important. I think we can see it here. Pretty fun. And
This is because it's like e in the power of e of I minus phi minus
yeah,
alpha.
basically this term
Is e by
fluctuates
Yeah.
like that very quickly. Okay. If alpha is big, even if alpha is not big actually.
And there is an exponent inside an exponent.
What?
It's an exponent powered by an exponent.
Yeah, so it's you do a lot of these, and then you have the sum of all of it. Big head. Yeah. So mathematicians just decided that a lot of fast fluctuation, sum of fast fluctuation in phase will be 0 unless some conditions of it, which is smart because I don't want to do it. Yeah. So we see that the average of the phase would be, according to this, because we said that the main contribution to the probability would be where the phase match. So the average, you can also safely assume, without me proving it even, would be where the phase is equal to the phase of alpha. But what's much more interesting is, and I'm not going to do any calculation of it, I'm going to argue that the standard deviation will be 1 over square root of 2, without any calculation. Why? Well, what is the standard deviation of the phase? So let's say, for example, in the Fock state, right? What will be the standard deviation? Well, if I want the standard deviation for the intensity, I'm going to look at where my intensity is and see how far I go in each direction, right? So intensity will be far away from the axis, the center of the graph, and closer to the center of the graph. In phase, we know that they're orthogonal, and we also, it's pretty clear to see in the circle that the phase standard deviation will go like this, right? But remember that last tutorial we drew and proved that the coherent state is basically a circle with a radius of 1 over square root of 2, or 1 over 2 if you're taking the variance instead of the standard deviation. It doesn't matter, right? So without even checking it, I know that if I'll measure the circle in this direction, which is the phase direction, it will also be 1 over square root of 2. we proved last tutorial that every quadrature of a coherent state has standard deviation of 1 over square root of 2. Also, interesting addition. If the noise is the standard deviation 1 over square root of 2, why strong lasers are very noisy?
Why strong lasers are
Yes.
very noisy.
You activate the laser and you see some fluctuation, and if you put more power into the laser, you see even bigger fluctuation.
Maybe because of the vacuum, or
And it's less apparent when you pump
No, it's actually a bit simpler. It's because what we'll have is that our every laser has what we call the single photon noise, which means that we mismatch by 1 photon, which is a vacuum-based effect. But when we actually measure it, we're taking the measurement squared. So if we have a field, for example, n, and we take it times some field with some noise, which the noise gave it +1, the answer will be n squared plus 1. The fact that we take intensity measurement, not field measurement, shows us a much bigger noise than the area that it has in the phase space. So the standard deviation that we saw in the quadrature is not the standard deviation that you're measuring, but you're actually measuring the laser itself. Yeah, if you want to impress Avi, tell him that you have 1 photon error in your laser. Yeah. Okay.
is like very small.
Very small. You just amplified by
Yeah.
a coherent intensity. All right. So this is the end for the intro for quantum states and quantum states of light. And now we're gonna do some practical stuff by talking about quantum correlation, a little bit of beam splitter. I don't know. Let's see how far we will manage to get.
the מערכת על כל אחרת כבר?
This is the next one. I'm pretty sure in the
wow.
pretty sure in the
Little bit of
website it's called the what?
A little bit of that and a little bit of this.
Yes. Pretty sure in the tutorial in the website it's called quantum coherence, something like that. Website.
נראה לי שלא יודע טוב.
לא, זה בסוף, זה ב3.
טוב, נראה לי לא יודע, אתה יכול לפתוח?
Again.
כן.
Damn you. ואז מה, מי יראה את זה כבר? שלום לצופים בבית, כאן אני שובר את הקיר הרביעי. ברוכים הבאים לתרגול.
How do I know what it's
שיט.
זה הודעה שנייה.
אז רגע, אם זה לא עובד, למה אתה מדבר באנגלית?
לא, זה עובד.
זה עובד? לא משנה.
מסתבר שזה מקליט אוטומטית בשעות האלה.
כה מעניין. ושומר את זה, אז כאילו אם אתה מבריז או עולה זה עדיין יהיה קיים.
לא, כי הזכירה תבדוק את זה.
Okay.
No, I'm not gonna. Okay, I upload it. There should also be homework, but I might upload the homework.
No.
כי יש את 3.
Yes, that's why I'm not uploading them right now.
No need for
Anyway, it's on the website. Okay.
אתה יכול לעלות כבר עכשיו, לא משנה. יהיה עוד איזה חודש.
לא תיקנתי תאריכים, אז נראה לי אחר כך. Alright, so we saw 2 tutorials maybe ago, 3 tutorials ago, I don't know, something that we can define for classical field it's no longer Facebook. We can define for classical field a coherence function g1 of tau equal to 0 tau. You might have a t here if the field is not stationary, but right? Well, we had some condition. G1 and G1 tau be equal to G1 minus tau conjugate, and we also had G2 tau equal to 0 conjugate tau is 0 times conjugate divided by e conjugate 0, e 0 plus squared. There's no total value here, but it's fine. Well, we also found that G2 of 0 to be equal or greater than 1, and for stationary light, light, G2 of 0 bigger or equal to G2 tau, and finally, again for stationary light, G2 of tau equal to 1 average I t plus tau divided by average t squared, where delta I of t equals I of t minus average I of t. Right? Now, the next step might be shocking. To take this to the quantum realm, what I'm going to do, I'll put hats. Hats on everything. Everyone get a hat. Woo! Everybody wants. Also, usually when you write fields in quantum mechanics, instead of writing field and conjugate, we write E plus, E minus, but it doesn't really matter. So I'm not gonna do it. But one more specific thing that's very important is that E quantum realm equal E0, some amplitude, times the annihilation operator, times some phase. Okay, the general. Of course, it's equal. Okay, if I'm. Let me also replace the stars with daggers because it's more professional. So stars. Dagger. So let's do an example just to see if we still understand the coherence. When we go to the quantum realm. So let's say we have a state psi is equal to 1 over the square root of 2 n plus 1 over the square root of 2 n plus 1. Right? G1. So to find G1. Okay. This would be equal to, we sum right here, but that's right. But instead of taking a general average, I'm taking an average of our state now. So psi E dagger T E plus tau psi E dagger of T E of T psi. Now E dagger of T E T plus tau would be equal to absolute value squared of T0, right, times A dagger A, right? The operator here. Times these terms will cancel each other out from the dagger, the non-dagger, and then this tau will just add a little bit of a phase term here. So e to the minus I omega tau. Okay. And of course, the bottom part will be exactly the same without this exponent. So we get that G1 of tau would be equal to right psi. This absolute value E0 absolute value square will cancel each other out from the two parts, and we're left with A dagger A psi divided by psi A dagger A psi e to the minus I omega tau. Right? Now, it's obvious, I think it's obvious to all of us that this would be the answer, but just will be just to make sure that we're all up to speed, up to snuff. Just put this down. Sine. Right. This would be B 1 over 2 n plus 1 A dagger A plus 1 n, right? We know that A dagger A will not change the number here, the numbers here, so we can completely separate them to n and n plus 1 and plus 1. And this A dagger A, we also know it is the number operator, just allow us to take the n out. So this would be equal to 1 over 2 n plus 1 plus n plus 1 over 2. This was pretty simple, nothing crazy here. Now let's do G2. Right? I'm going to keep the equation for G2 just for simplicity. The denominator we already know what is it. The denominator would be, so overall the denominator here, this would be equal to absolute value is yours to the power of 4 times n plus 1 over 2 squared. This is enough for now. Now for the denominator would be E dagger T E dagger T plus tau E T plus tau E T. I can write everything that's on the notebook, all the steps, but I think it will be much quicker to notice that this one will have a certain phase that's called x, and this one will have a minus x phase. That's also the terms on the opposite side. So they will have no phase terms. Plus we'll get E0 absolute value to the power of 4. So since we have 4 terms here, and counting the operators inside, we have A dagger, A. Alright? So denominator, where is it here?
Denominator.
So in the end, it's gonna equal n minus 1 divided by n. We'll see.
Denominator equal, I don't want to write this stuff again. E0 to the power of 4 psi A dagger A psi, right? Which would be equal to, let's just take this part. This part will be easier, just look at this one. Right, so A dagger A psi, I'm just going to replace it with n plus 1. We would remember what are you doing?
Nothing.
We will remember the 1/2 later. Trust me. Right? So let's start with the annihilation operator. This will reduce it by 1 and then the square root of n, then reduce it by 1 again and the square root of n minus 1 will be square root of n minus 1, n minus 2. Alright? Plus the same way n plus 1, n minus 1, right? And then 2 creation operator will give us square root of n minus 1, n minus 2, n minus 1, right? No, sorry, this one is n minus 1, n.
This is n. N times n minus 1.
So v times n plus square root of n plus 1.
No. You can remove the square root.
Yes, I will do it.
Just delete it with your finger.
Just be. No, I don't wanna. You can't make me.
That's right.
Right? So overall, I'm gonna get my eraser again. Did Avi do a beam splitter with you yet?
No.
No.
He wanted to do it, and then he said, "Nah, we don't have time right now. We will do it in the next lesson."
So I don't know if I can do it.
You can do it. It's not recorded. It's off the record.
So the n will go with the n plus 1 will go with the n plus 1. And
We don't have to.
we get absolute value is 0 to the power 4 of n minus 1 plus n plus 1. So it will just be the value is 0 to the power 4 n squared. So G2 of tau. Oh, that's the ring 2. Tau. Thank you. Will equal. I will this n to the power 4 will cancel out this n to the power 4. We get squared divided by n plus 1/2 squared. Weird, right?
Okay.
Why is it weird? You back there with the hat. Not you. Do you know it all? Why is it weird?
תחשוב. אתה זוכר על G2, מה אמרת?
כן, כן, כן. It's not equal 1.
It's smaller than 1.
No, it's weird that you got, with Avi, we got 1 minus 1 over n, and you got this.
I don't know, it's dependent on what states and stuff like that. So we got some interesting result that we have G2 that is smaller than 1. Some correlation in intensity that it's below Pearsonian statistics, which is the first taste that you get right now for squeezing or entanglement, stuff like that. It's right here.
Okay.
It basically comes because a lot of processes or a lot of way of writing, like how I wrote my state here, sort of put a constraint on our statistical space. I don't want to go too deep into it because we will go into entanglement and into squeezing and all of that, and we'll see it better. So I don't want to really go deep into it. Now, my question is, let's see what's the time? 7.
It's a great time to stop.
Yeah, the next part is okay. The next part that I wanted to do is to take what we learned here and apply it on a beam splitter, and measurement through a beam splitter, to show a bit of correlation, or practice a little bit of quantum states, and I think we'll save it for next tutorial, because if Avi didn't start, if Avi didn't do the beam splitter, I shouldn't really, even though I really want to, because it's something real cool to see there. Also, the beam splitter is the first time I just noticed the first time that we're really gonna talk and see in action the vacuum and the meaning of having a vacuum in the.
They talked about it like a little bit, that in the beam splitter you have one enter is the laser and the other enter is the vacuum.
Yes. We'll prove in this tutorial, the proof of it is really, really quick, that you have to have a second port, so a beam splitter, and you have to consider the vacuum in order to keep your probabilities equal to 1, and you keep your computation relation, why am I always blanking on this? You don't know.
Commutator.
Commutators, thank you.
Yeah.
I don't know what's the word from.
Commutation.
Yeah.
אתה יודע מתי גילו את הוואקום fluctuations?
Probably a long time ago, for quantum mechanics. Probably.
Really?
מה לדעתך?
There's a lot of effects that we found out about them before quantum mechanics. We didn't have a lot of explanation, or we had explanation that eventually were proven false. Quantum mechanics showed its head a long time, we just didn't know about it.
פוטו-דטקטורים קודם, או vacuum fluctuations קודם?
What do you mean?
What happened
אבי אמר
first?
למשל בבין ספליטר שאתה מכניס רק מכיוון אחד, אתה לא אמור לראות כאילו, זהו, המציאות אתה כן רואה את הפלקצואציות האלה. השאלה שלי, אם הראשון שבדק את זה לא הבין מה הולך שם, הוא אמר שזה רעש, או שהוא ידע שיש איזה אפקט?
I think early on, specifically for photo detection theory, I think early on people just chucked it out to noise, all that kind of stuff. You can also see that a lot of the building blocks from quantum mechanics didn't come from photo detectors. It came from other problems that didn't have quite a defined answer. For example, back body radiation was a really big start for quantum mechanics. In material, like in physical matter, there's the spin question of electrons, which was also a big step in the beginning of quantum mechanics. You know, you shoot atoms and you see different paths, which can only be explained later by spin. Which, by the way, a spin of an electron is not an electron with this. It's some field-related property that it's not. I never saw someone visually demonstrate what a spin is. It's just a weird property that relates to some. Does relate to angular momentum, but it's not spinning.
אז אתה אומר שהם ראו תופעה שהם לא הבינו מה היא ולמה היא קורית.
קראו לזה רעש.
There's a lot of stuff that developed in physics by. There's a lot of stuff developed in physics by someone doing almost usually a random experiment and then getting weird results, and we're like, I don't know.
It's like when we work in the lab, everything is noise. Everything is just noise.
I actually wrote a nice presentation. I think it was a nice presentation about
In the military.
about cosmic background radiation, and this was started by people trying to two scientists. I forget their names. Two scientists trying to map out the infrared mapping of the sky, doing infrared mapping of space, and they expected that there will be a lot of dead zones because most of space is empty. But they saw actually quite bright noise everywhere. Initially, they thought that it was because there were birds in the antennas. Back then, the antennas was like a big, huge thing. They thought that they had birds in their antenna that pooped on their instrument, and that created a noise. But then they cleaned it, and they still saw that noise. So they tried to figure out what it was, and then they went back to classical astrophysics and looked at atom measurements in space and saw that something doesn't end up. And eventually they came up to a different conclusion, that this is some leftover radiation for the creation of the universe. And from that radiation, they also managed to calculate like the temperature and the beginning of time and the expansion rate of the universe was also weird stuff. just because again they did an experiment and they saw results that didn't make any fucking sense. And that's a lot of physics. That's a lot of physics.
It's a lot of physics.
It's either that or someone
Just mess with them.
just in physics discoveries are either that or someone thinking about a really weird model which works out, like Einstein. Einstein didn't have a like